Hi, this is Arnesh Bose, and I'm a PhD student at the Electrical and Computer Engineering Department at Western Michigan University in Kalamazoo, Michigan, USA. Today, on behalf of my authors, I'll be presenting a paper titled A Novel and Flexible Microplasma Discharge Device for Inactivating Pathogens Suspended in Fluids, and IEEE International Conference on Flexible Printable Sensors and Systems in 2021. Disinfection and inactivation is the process of eliminating microorganisms on surfaces or in fluid media. According to World Health Organization, almost 500,000 people die due to various waterborne diseases worldwide each year. Excessive addition of chlorine poses a health risk, and a heat-based disinfection requires high temperature and is a slow process. UV-based disinfection devices operate in ambient conditions, utilizes no chemicals, and have no discharge byproducts. Commercial-based UV lamps operate in a single wavelength, thereby limiting its efficacy for disinfecting a large variety of bacteria. Microplasma or non-thermal plasma are stable microscale glow discharges and provide a wide range of UV wavelength and operate in air. Now I'm going to be talking about the device fabrication, and for that we use Universal Laser System PLS 6MW for fabricating the MDD device. So initially we put used a 2 mil PET film that was cleaned with IPA, and then we put 2 mil copper tape that was then attached on one side of the PET film, and a honeycomb design was patterned with an overall diameter of 31 millimeter using a laser ablation from the top electrode. The 2 mil single-sided cap and tape was then attached on the opposite side of the PET film, avoiding the short circuit between the top and bottom electrodes caused due to perforation created in the PET film during the laser ablation process. Finally, another copper tape was laser ablated to 33 millimeter diameter to form bottom electrode and attached onto the capped on tape. The total thickness of the device was 8 mil, and the fully fabricated device in its off and on stage is shown on the right. Now we're discussing about the experiment setup and results. On the left, you can see the experiment setup, where we have a variable DC input power supply, which was connected to a DC to AC inverter, and then was connected to the MDD. A stir bar was placed inside the Petri dish that was filled with bacteria suspended in PBS solution. The Petri dish was then placed on top of a stir plate and operated at ambient temperature. The MDD with polystyrene platform was placed over the Petri dish, and the distance between the surface of the PBS solution to the MDD was kept constant at 4 millimeter. The efficacy of the MDD disinfection for treatment time of 1 minute to 10 minutes were tested, and then after exposing the bacteria to microplasma, 100 microliter of the treated bacterial suspension was pipetted and serial diluted to determine the CFU on LB agar plates Petri dishes. The Petri dishes were then incubated at 37 degrees Celsius for 16 hours, and the CFUs were then counted to determine the efficacy of the MDD. And as you can see, as compared to the control mark to 0, we have an 8-log reduction when the treatment time was increased to 8.5 minutes. So we can say 8.5 minutes is sufficient to, at 10 volts, is sufficient to disinfect the bacteria in suspended in previous solution. And on the graph on the right, we can see the MDD being compared in its flat state to 25 and 50 millimeter radius of curvature, and the power density was calculated. So the total spread of microplasma from this on the surface of the device was around 1 millimeter, and then the total area of the microplasma discharge was calculated as 4.34 centimeters squared. And then, as we can see, then we compared the power density on the curved surfaces as compared to flat surfaces, and it was evident that the slope of the linear fits was 0.178, 0.179, 0.180 for flat, 25 millimeter, and 50 millimeter respectively. From the results, it can be concluded that the MDD is flexible and can be operated on curved surfaces. So concluding our work, you can say that the flexible MDD was successfully fabricated for disinfecting Pseudomonas, aeruginosa, and then an 8-log reduction in bacterial viability was achieved when the MDD was activated for 8.5 minutes at an input voltage of 10 V. Further research is in progress to demonstrate the capability of the device to disinfect other pathogens, including gram-negative bacteria such as E. coli, and also gram-positive bacteria, including Staphylococcus aureus, and spore-forming Bacillus subtilis. The authors would sincerely thank the Department of Biological Sciences, Electrical Engineering and Computer Science Department, and the Center for Advanced Smart Sensors and Structures for the support for the successful completion of this project. Thank you for listening. And if you have any questions, please feel free to email me. And thank you and have a good day.